Let me start by welcoming Natarajan Meghanathan, who is a professor of computer science at Jackson State University. He has been working with us now for, I would say, good 7, 8 years or so, early on during the project on network science and the new version of network science work, as well as the expeditions work. And he's going to talk about some interesting results he recently has obtained on computing properties of networks. So over to you, Meg. Thank you very much for doing this.
Thanks, Madhav. Good morning, everyone. So my topic today is neighborhood-based bridge node centrality tuple for complex network analysis. Traditionally, there's been only centrality metrics, which are like scalar quantities like degree centrality, between centrality, and so on, to capture the topological importance of nodes. So this is the kind of first work where we introduced a tuple, means more than one entries to capture the centrality role played by nodes. And specifically, you're targeting bridge nodes. That's the thing you're looking now. So a bridge node is a node whose neighbor nodes are going to be sparsely connected to each other. And if you remove this bridge node, the neighbor nodes are going to likely get disconnected into different components. They could be part of different clusters, like for example here for the same graph. So if you look at node 5, its neighbor nodes like 1 is in one cluster, 0, 6, 9 in another cluster, 7 is in another cluster, and so on. So if you remove 5 from this graph, this is what's going to happen. So its neighbors get disconnected into different components. So that makes this node 5 to be more qualified for the role of a bridge node. On the other hand, if you look at node 1 here, if you remove node 1 and of course remove the links connected to it, then its neighbors are still kind of connected. Of course, they are connected or reachable through longer paths, but still just reachable. So from a bridge node point of view, I would prefer to rank node 5 higher as a bridge node compared to node 1. In the related work, I have listed here a collection of 8 metrics. Unfortunately, almost all of them rank node 1 almost the same as node 5 or sometimes above node 5. So that's a kind of motivation. Those works fail to capture this definition of a bridge node. That is, if it connects the neighbors who are sparsely connected to each other, and if you remove this node, the neighbors get disconnected. And such a role is not captured by the existing centrality metrics out there. And bridge nodes are very useful for different applications. For example, from the epidemiology point of view, if you have this as the employees in an organization, and you want to decide which nodes I need to vaccinate so that we can achieve herd immunity in the sense that the non-vaccinated nodes are protected by the vaccinated nodes. If you randomly pick, say, 2 nodes that you want to vaccinate out of these 10 nodes, and if you pick, say, 0 and 9, that's not going to do anything for the other nodes. They're still going to get infected. If some node gets infected, the infection is going to spread. On the other hand, if you vaccinate node 5 and node 3, which we will see later, or the 2 top-ranked bridge nodes for this graph, then if any infection happens in this cluster of 1 to 4, it's going to spread only to 6. So basically 1, 2, 4, 6 are going to be infected, and 3 and 5 are vaccinated. So that means the infection is not going to spread to 0 or 9 or 7 or 8. So 5 and 3 can provide this herd immunity to the non-vaccinated nodes. So that's one application, the bridge. So this centrality tuple that we're going to look at can be used to identify what nodes need to be preferentially vaccinated. And a lot of similar applications. An opposite for epidemic spread is information spread, which will be some information cascade. So again, if you choose the bridge nodes as the initial adopters for the decision, then they can propagate that information further down into their clusters you're part of. For communication networks, you can again choose the bridge nodes as cluster heads and go about clustering-based communication protocols. And also in social networks, the bridge nodes could provide acquaintance to people who don't know each other. So again, going back to this example, 0 and 9 work with 5. They don't work with anybody else, but 5 works with 7 and 6. So 5 can provide this acquaintance to 0 and 9 to collaborate with 7. So a lot of such applications are possible once you are able to properly identify and rank the nodes as bridge nodes. As you can see, the role of bridge nodes is kind of getting complex because it's not one particular role they're having. So we could classify the role into three categories like bridge hub node, bridge border node, and between clusters node. So what I mean by that is here. So again, we don't need to run any clustering algorithms, but I just show the clusters to illustrate the idea. So if we run, say, a traditional clustering algorithm like Louvain or something on this graph, it partitions this graph into these three clusters. So this node 5 provides the connectivity for this nodes 0, 6, and 9 to the rest of the nodes within the cluster. So from that point of view, it acts like a hub node. And then node 5 is also connecting this cluster. So we can call this a home cluster. So it's connecting its home cluster 0 with the other clusters like cluster 2 and cluster 1 through the edges connected to node 5. So especially to cluster 1, there's no connection for cluster 0 to cluster 1 other than this through node 5. And sometimes it can also function as a between clusters node. Like, for example, if you want to communicate from cluster 2 to cluster 1, especially if some nodes in this cluster are not working, then this bridge node 5 can act as a between cluster node, facilitating communication between two clusters. So it's not possible to have one single metric to capture all these roles. So that's why it's again a motivation that we need to have a tuple to capture this role of node as a bridge node. So here I just list some nodes in this graph and say to what extent they play the role of these three nodes, bridge hub or bridge border, bridge between clusters. So like node 1 here, it's not really a hub node because these nodes 2, 3, 4 are still reachable to each other directly. So they don't need to go through node 1, whereas node 5 is a hub node for its cluster. And it's a border node as well because it provides connectivity to other clusters. So in that way, it's a border node. But node 1 is a weak border node because this cluster can still get connected to the other clusters to node 2 or node 3 and so on. And also, these two clusters are directly connected to each other. So node 1 is not really going to play as a between cluster node. So I'm again highlighting node 1 here in comparison to node 5 because existing metrics rank node 1 very highly as a bridge node on this graph. So just as a review of what is available so far, so these are the very classical centrality metrics, the neighborhood-based degree centrality or eigenvector centrality and between centrality and closest centrality. So these are just scalar quantities, just one number quantifying the role of a node for what they're supposed to quantify. So the degree is the number of neighbors, eigenvector is the measure of the node as well as the degree of its neighbors, between is fraction of shortest path going through a certain node, and then how close is the node to the rest of the node. So they just quantify one particular thing, not like a very complex role like what we just saw for bridge nodes. And these are some of what's available in the literature to capture the quantify the role of a bridge node. As you can see, some of this are community aware. That means you have to run a clustering algorithm or a community detection algorithm on the graph and then identify the bridge nodes. And some are community unaware. That means you don't have to run a clustering algorithm or community detection algorithm. These metrics can themselves be able to quantify the role as a bridge node. And between centrality is one among them. So if a node facilitates communication between several other nodes, it could be considered as a bridge node as well. But as you can see, nodes like 7 and 8 in this graph that I showed here may have a high betweenness, but they are not functioning as a hub node or a border node and so on. So that's where betweenness centrality alone cannot be metric to quantify bridge nodes. In order to proceed further with the algorithm and the quantification process, so I use this notion of algebraic connectivity of a graph. And algebraic connectivity basically tries to quantify the extent with which a graph is connected. So as you can see, this graph is connected, but we want to quantify how much it's connected. So one way to do that is using algebraic connectivity. And so for that, we need to determine what's called this Laplacian matrix for a graph, which is basically the diagonal represents the degree of the vertices. And if the pair doesn't have an edge, the entries are a 0. And if they have an edge, the entries is a -1. And then you run a spectral analysis, determine the eigenvalues and eigenvectors of this matrix. And we're just interested in the eigenvalues here. So for a 10 vertex graph, you're going to get 10 eigenvalues. And a good property of Laplacian matrix is the eigenvalues that will get us output will automatically be sorted in the increasing order, and the number of zeros represents the number of components in this graph. And as you can see, this whole graph is connected, so it's only one component, so it's only 1 0. So the first non-zero eigenvalue represents the algebraic connectivity of the graph. So it's a measure of the connectivity of the graph. So this graph has 10 vertices, so this could be close to as large as 10 if the graph is almost close to a complete graph. So in a scale of, say, 0 to 10, we can see where 0.6536 stands. So it's not very highly connected. For example, if you remove node 5, some nodes get disconnected from the rest. So that talks about the connectivity or the extent of sparseness in the graph. We are going to use this notion of neighborhood graph to determine this tuple. So you don't need to have the global knowledge. You just need to have a local knowledge, just a neighborhood knowledge of the nodes. So this algorithm can be run in parallel at each node, and each node can come up with the centrality tuple of itself. So I'll just show a couple of cases, and we'll use this graph as a running example graph in this presentation. We are going to construct what's called the neighborhood graph for each node. And say for node 5, it's basically its neighbors are going to be the vertices in that neighborhood graph, and the edges connecting the neighbors. So 0, 9, 6, 1, and 7 are the neighbors of 5. And if you remove node 5, basically this is what is a neighborhood graph. The edges connecting the neighbors of node 5. So you could run this graph through spectral analysis, and this is the Laplacian matrix for this graph. And as you can see, this is not connected, and it has 4 components. So the number of zeros among the eigenvalues is 4 zeros. So that indicates it has 4 components in the neighborhood graph. Whereas this is the neighborhood graph of node 1. If you remove node 1, this is how its neighbors are connected. So this is a connected graph. So if you determine the eigenvalues for this Laplacian matrix, there's only 1 0. So the first non-zero value is the algebraic connectivity. So if the neighborhood graph is connected, you're going to have a non-zero value for algebraic connectivity. If the neighborhood graph is not connected, you're going to have 0 as the algebraic connectivity. So this centrality tuple has 3 components in it. The first entry is a number of components in the neighborhood graph. So in this case, for node 5, the number of components is going to be 4. In the case of node 1, it's going to be 1. The second entry is the algebraic connectivity ratio of the neighborhood graph. So the ratio is basically the algebraic connectivity of the neighborhood graph divided by the number of nodes in the graph. So in the case of node 1, it's going to be the 0.5188 divided by 5, because there are 5 neighbors for node 1. So that's going to be around 0.1 something. So that's the algebraic connectivity ratio. And the third entry is basically the number of neighbors, which is the degree of that vertex. So these 3 things put together, I propose or formulate this as the neighborhood-based bridge node centrality tuple for any node. So as we can see, if the number of components is greater than 1, that means the graph is not connected, then the algebraic connectivity ratio is going to be 0. On the other hand, if the number of components is 1, the algebraic connectivity ratio will be something greater than 0. But if a node has only 1 neighbor, that's a special case, that node is considered to be connected to itself. So the algebraic connectivity ratio will be like 1. And I'll show this case when we go through the numbers here. So these are the centrality tuples for all these nodes here. And I was talking about nodes like 0 or 9. So for either 0 or 9, its neighborhood graph, if you remove 0, it's going to be just 5 on its own. That's the only vertex in the neighborhood graph. And any vertex is considered to be connected to itself. So in the case of 0 or 9, the first entry, which is the number of components, which is just 5 on itself. And again, since there's only 1 vertex in the neighborhood graph, its connectivity ratio is 1, and the number of neighbors, which is also 1. So that's how these 2 vertices, 0 and 9, get the centrality tuple. On the other hand, for node 5, it has 4 components. This neighborhood graph is not connected, and it has 5 neighbors. For node 1, as I said, it has just 1 component, and it has a non-zero algebraic connectivity, and that 0.5 something we saw divided by number of vertices 5, 0.1038, and the 5 neighbors. So this is what will form the centrality tuple for the vertices in this graph. So now we need to have a ranking formula to rank the nodes to say to what extent they play the role of a bridge node. So this is rules for ranking. We want to say a vertex V is ranked above vertex U as a bridge node, and we indicate that NBNC of node V is kind of greater than NBNC of node U. So V is ranked above node U according to these rules. So the priority goes to the first entry in this tuple. So if a node has more components in its neighborhood graph, that means it's bringing together all its neighbors. And if the node is removed, it disconnects its neighbors. That's like node 5 that we saw in the graph. And if there's a tie in the number of components in the neighborhood graph, then we give preference to the second entry. If the algebraic connectivity ratio for a vertex is V is less than that of vertex U. So they are tied on the basis of the first entry, which is the number of components in the neighborhood graph. So then we go to the second entry. So again, we want to give preference for nodes that is having a sparse neighborhood. That node will play the bridge node role more strongly compared to a node that has a dense neighborhood. So if the algebraic connectivity ratio is smaller for the neighborhood graph, then that node should be ranked higher compared to a node that has a relatively larger algebraic connectivity ratio. Now, if the nodes are tied on the first two entries, then we break the tie by making use of the degree of the node, which is the number of neighbors in the neighborhood graph. So a node that has a larger degree is considered to be ranked higher than the node that has a smaller degree. Now, still there could be a tie, as you can see here. So according to those rules, this is a kind of tentative ranking of the nodes, unique rank number. But still, like you see, 7 and 8, they have all the three entries the same. So the final rank will be the average of the tentative ranks. So they are equally ranked. And then similarly, 9 and 0, they have all these three entries the same. So the final rank is the average of the tentative rank. So this is an approach we also use for Spearman's rank-based correlation coefficient to find the tentative rank, unique rank numbers. And then if there's a tie, we just average out all the tentative ranks for the tied nodes. And that's the same idea I use here to get the final rank. Again, if you go back to the definition and those three roles I mentioned earlier, so the bridge nodes can be like a hub node, border node, between clusters node, or more than one of these roles. So the first entry, which is the number of components in the neighborhood graph, captures all these three positions of a node as a bridge node because it brings together its neighbors within the cluster if they are sparsely connected otherwise. In that way, it functions as hub node. So if you remove that node and the neighbors get disconnected to different components, then it means it can also function as a border node. And then again, it provides connectivity across clusters. If the neighbors are part of different clusters, then it provides connectivity between the two clusters of the neighbor nodes. So the first entry is capturing, as in essence, all these three. And if there's a tie, then we go to the second term, which is the algebraic connectivity ratio. So that captures the extent in which it bridges the sparseness within the cluster, like a hub node. And the third term, again, if a node has a larger degree, it brings together its neighbors. And again, the nodes having larger number of components and the lower connectivity ratio are more likely to also have a larger degree. So they are kind of related to each other. So if you go back to this example again, you see node 5 essentially in this graph captures all these things. It has more components in its neighborhood, zero connectivity in a neighborhood graph, and it has more degree. So it brings together all these three things. There's node 1, which is somewhere here. It's ranked well below node 5 in this, according to this metric. So then I want to focus on the performance now. The first thing I want to talk about is time complexity. So as I said, this is something locally computable. We don't need to have the global knowledge of the entire graph at any node. So this is a very fundamental definition of average degree. If you know the number of edges and number of vertices in a graph, the average degree for any vertex is 2m over n, 2 times the number of links divided by, and then for undirected graph. If you want to compute the eigenvalues for this Laplacian matrix for an n by n graph, it's big O of n squared time. But we are not computing for the entire graph. We are just computing for the neighborhood graph. So the reason why I brought out average degree is the average degree of a vertex represents for us now on average the number of vertices in the neighborhood graph. So we are going to have neighborhood graphs of size 2m or n by 2 vertices. The computation time for the eigenvalues for this Laplacian matrix for this neighborhood graph is going to be 2m over n squared. So it's like m squared over n squared time complexity. Each node can run this in parallel. If parallel computation is possible, then that will be the time complexity to compute this bridge node centrality tuple for all the nodes. If you have to do it in a centralized fashion, then we have to multiply this term by n, the number of vertices. So it's going to be m squared over n. So as we can see here, we don't need to run any clustering algorithm because one traditional or easier way to, as I showed in the earlier graph, is to run a clustering algorithm like Louvain or any clustering algorithm and identify nodes that are connected to one cluster, but also connected to other clusters. So that's one very naive approach to identify the bridge nodes of a graph. But as you saw, we don't need to run any clustering algorithm in order to quantify or identify the bridge nodes. So how this time complexity compares to the existing clustering algorithms, if you go to the clustering approach, the Louvain is one of the lowest time complexity community detection algorithm as like n log n. And the other computation algorithms like Irwin, Newman, and or the greedy modularity, spectral clustering, all these things are n square, n cube time complexity. Now, I evaluated this approach with 50 real-world networks, and a lot of benchmarking networks like Karate Club Network, Football Network, and all these things are included here. On the basis of time complexity, the yellow colors indicate that the n log n term. So Louvain time complexity n log n is the smallest for all the computation algorithms out there. So I use that as a reference for comparison with this 4m square over n square, which is the time complexity if you do this in parallel, if you compute this centrality tuple in parallel. So the real-world networks for which we have a highlighted yellow color are those networks for which n log n is greater than 4m square over n square. Of course, we know the number of vertices and number of edges for the graphs. So out of these 50 networks, only few of them, like less than 15, I have this yellow highlighted. So if it's not highlighted, that means the 4m square over n square is less than n log n. So that means bridge node centrality tuple can be computed faster than the Louvain clusters. Now, the second metric which we use for the evaluation is effectiveness. We are proposing this as an alternate to the existing approaches for identifying bridge nodes. Again, one way to test as a brute force approach, if your node is a bridge node, if you remove that node, the graph should get disconnected. So I use this approach to test effectiveness. So we rank the bridge nodes according to this tuple. Likewise, for any metric out there, we can rank the nodes on the basis of the values that metric is capturing. So then we remove the nodes in this order, the top rank bridge nodes. We remove them and find out the size of the largest component. And we wait until the fraction of the vertices in the largest component becomes less than 0.05. So we keep removing the bridge nodes in the order of the ranking until the size of the largest connected component is getting less than 0.05. That's like what I use as a threshold. So if you're able to remove very few nodes and disconnect the network and bring the size of the largest connected component to just like 5% or less, that means your approach is very effective. You don't have to remove a lot of nodes in order to bring down the connectivity of the largest component to this number. So the fraction of the top rank bridge nodes, I call it as rho min, that need to be removed in order to bring down the fraction of nodes in the largest connected component to less than 5%, then that approach is very effective. Again, for the 50 networks and the 8 metrics out there, I compare the fraction of bridge nodes that need to be removed in order to bring down the fraction of nodes in the largest component to be less than 0.05. So again, use a highlight yellow color to indicate which approach is having the rho min value to be smaller, because we want to remove fewer vertices and bring down the fraction of vertices to connect to the largest component less than 5%. The NBNC tuple has a lot of yellow colors, this first column. That means it's very effective for several real-world networks compared to the existing metrics. And the existing metrics are also effective for certain real-world networks, as you can see the yellow colors for them. But overall, NBNC tuple is more effective compared to the existing metrics. So again, that means with the existing matrix, you have to remove more bridge nodes. So for example, for network number 26, you have to remove almost 90% of the top rank bridge nodes in order to bring the fraction of nodes to the largest component less than 5%, whereas you remove only 77% of the top rank bridge nodes and so on. So the third metric uses efficiency or accuracy. As I said, this could serve as an alternate to clustering algorithm. So we are not running any clustering algorithm to determine the number of components. So how close is the number of components in the neighborhood graph to the actual number of clusters in the neighborhood of a node? So for example, if you run the Louvain algorithm on this graph, you can see for node 5, it has 2 neighboring clusters and it's on its own cluster. So basically, neighbors of node 5 are in basically 3 clusters, this cluster and one cluster, so 3 clusters. But if you go back to NBNC tuple for node 5, it has 4 components. So according to our tuple, we are predicting that the neighborhood of node 5, it has 4 clusters. That's what the number of components in the neighborhood graph indicates. Whereas if you run clustering algorithm on this graph, it says that its neighbors are at 3 clusters. So how close are these 2 numbers? So we want our prediction or our identification of the number of components to be same as the number of clusters in which the neighbors of a vertex are part of. So we determine the root mean square error of the difference between these 2 numbers and average it out for the number of nodes. So the number 0.4 in this example graph indicates that the difference between the number of components that we identify in the neighborhood for a node based on this tuple compared to the actual number of clusters in which the neighbors of a node are part of is like plus or minus 0.4 on average. That's what the root mean square error indicates. And if you do this similar calculations for all the 50 real world networks, so you can see like for 13 out of 15 networks, the difference is root mean square is between 0.5 and 1. And it doesn't go above 4 and keeps decreasing as the root mean square values increase. The number of networks for which you observe such values is going down. So that means it's also more effective in identifying the number of clusters in which the neighbors of a node are part of. And we are able to do that without running any clustering algorithm. Just by locally running this Laplacian, the spectral analysis on the neighborhood graph, we are able to predict the number of clusters in which the neighbors of a node will be part of. The last one is uniqueness. So in order to again highlight that this approach is identifying the bridge nodes in a certain way that is not done by the existing metrics. Again, as I said, we can rank the nodes based on the tuple and the other metrics as well. And I found the Spearman's rank-based correlation coefficient of these rankings. And if the correlation coefficient is between, say, negative 0.4 and 0.4, I said it's a very weak correlation, or it's close to 1 or close to negative 1, that's a strong correlation. A strong correlation for several real-world networks is like a negative thing because then we are proposing something that can be identified using existing metrics. On the other hand, if we have a weak correlation, that means we are proposing a metric that is identifying something that's not identified by the existing metrics. Again, for the 50 real-world networks, so these are the Spearman's rank-based correlation coefficient numbers with the community-aware metrics and the community-unaware metrics. So the pink color is for weak correlation or very weak correlation. So the correlation coefficient is between negative 0.4 and positive 0.4. And the green colors are the strong correlation. So majority of these cells have the pink color, especially in the community-aware metrics. And even among the community-unaware metrics, there's not that much green. It's either pink or it's like moderate correlation. So the networks actually, as the number of nodes in the networks keeps increasing. That's how I numbered the networks from 1 to 50. So as you increase the number of nodes, you can see actually is a weak correlation between the tuple and the existing metrics, but for both community-aware and community-unaware metrics. In conclusion, so what are we contributing through this work? So we propose a centrality tuple. So is there no tuple so far? Actually, the way that people have been forming tuple or like a vector is using a collection of the centrality metrics. So some works have put together betweeners and degree and all these centrality metrics together, and they call it a vector. So they use existing metrics and put together as a vector. So whereas this is the first time we are quantifying a tuple from scratch. without using any of the existing centrality metrics. And it can be used to rank the nodes as a bridge node, such that all these three roles, like a hub, bridge hub, or a bridge border node, or bridge between clusters nodes, are comprehensively captured. Metrics like betweenness, centrality capture the role of just a between cluster. It doesn't capture the role of a hub node or a border node, and like that. So this approach captures comprehensively all these three roles. And also is locally computable, so we don't need to know the global knowledge. And it can be also like an alternative to clustering algorithms or community detection algorithms. It can be used to identify the number of clusters or communities in which the neighbors of a node can be part of, without running any community detection or a clustering algorithm. So that way, it's also a unique idea. So this work has been published in the Applied Network Science Journal last year, and the funding support of this grant was acknowledged in this publication.
Thanks, Meg. So I had a couple of questions, but I'll let others ask first, and then I can ask. Thank you very much for the talk, Bill.
Welcome.
I have a question. Is there a way that you can adapt your parameter or your tuple for something particular? So for example, say you were interested in removing the edges between communities, that was more important, say, than removing edges within a community. Is there some way you can reformulate this to skew it? So of your three parameters that you used for your motivation, that your metric could skew in one of those directions, depending on what was most important?
Yeah, so this approach actually doesn't distinguish between edges as within a community. As I said, it doesn't, first of all, determine communities. So it treats all the edges equally. Of course, if you want to do like what you're telling, then we have to know what edges are really between communities and then remove those and do this analysis. Of course, yes, if we know that, yes, we can repeat the same process just by removing those edges and see how the connectivity and everything comes out. But as I said, this approach doesn't require that knowledge to what edges within a community or between two communities.
Thank you.
Interesting work. I want to ask you, have you done any experiments on comparing, let's say, the vaccination benefits of this? Well, first of all, I guess I should ask, you have a ranking of the nodes. Would that be used in actually choosing nodes for vaccination? For example, if I'm imagining a threshold model running on this network, would you?
Yeah. Yes, that's actually what I should have done as a future work after last year. But yeah, so as you suggested, we could, say, for example, take this ranking over here and run the SIS or SIR model, making some nodes to be infected and allow that infection to spread. I have just on an example graph, I have a simulation I did for my epidemics course, which I taught last summer, but I didn't do it on the real world networks and publish that work. Actually, what I observed is this. Once you vaccinate, say, 3 or 5, and even the infection starts with node 1, as I said, it does spread within this cluster, these four nodes. It doesn't spread to other clusters. And with these models, eventually the nodes recover and there's no new infection. So the infection kind of dies down on its own. It doesn't spread to the other nodes. But as you suggested, it will be good to see, again, how the top-ranked bridge nodes provide this herd immunity to the nodes which are not vaccinated. So we can play with the parameters, fraction of nodes that are vaccinated, not vaccinated, and run this SIR, SIS models and run some experiments on that and see, like this rho min, which I did here for the effectiveness. I can similarly come up with how effective it's in providing this herd immunity to the non-vaccinated nodes. Thanks for
that you're making, Natarajan, that all the edges are the same probability, because otherwise, if some edges have much larger probabilities of transmission, then you may have to worry about those values also, right?
Yes. So we can simplify, reduce the number of parameters by assuming all edges have equal probability of spreading the infection. So the bridge node, the edges are still considered to be equal probability. So if a node is vaccinated, we are assuming that that node doesn't get infected. So if the node is not infected, say, for example, if 1 is infected, 5 is not going to get infected because it's vaccinated.
Exactly.
So if 0 and 9 are not vaccinated, they are not going to get infected because the only way they can get infected is through node 5. And if node 5 is vaccinated and not infected, then 0 and 9 are protected.
Thanks, Natarajan.
Welcome.
Natarajan and Madhav here. Good talk again. And I think my question is very related to Ravi's question. In fact, I was going to ask that. But one thing we could do, if you would like, first of all, we have some larger networks that we have built now, which are synthetic networks for the, say, state of Virginia or a county in Virginia, which we can share with you. And you might be able to run your algorithm and identify top K nodes of high centrality, based the measure being your measure. And then we can actually run it through either CSONET system that Ravi and Chris and others have, or we can run it through our epi-hyper simulator to see how it performs with respect to vaccination strategies. So
Sure.
I think we can use a realistic network and we can use realistic disease model to try out if that interests you, because I think it would be a good exercise. But my other question is somewhat technical. I like your definition, but it appears that I didn't see a formal definition. And one formal definition I was thinking as I was going through your presentation was one in which you remove nodes or delete nodes such that not just the average shortest path lengths between pairs of nodes increases, but also there is something more. You also want the smallest shortest path distance to become as large as possible. Is that a fair definition? Of course, there are other constraints we can add, but it seems to be the closest to your example that you are trying to show.
Yes. Yeah, so either the neighbors are disconnected or the length of the shortest path between the neighbors increases as large as possible.
Right. But we want this average, but we also, because, some of them become infinity, then that doesn't get picked up. We also want some metric of pairwise distances to be played out, in a meaningful way. So worth defining it, I think, so in form to see what happens, because Ravi and myself had looked at other node deletion problems in the past in trying to improve, say, quality of or augmenting the networks to improve the quality of the network structure. So, and Anil has done some work which is also related, which I think we should talk to Anil on the spectral representation of these networks to understand disease spread. But thanks. Yeah, I just thought that it's an interesting measure.
Okay, thank you.
Thank you for a very good talk. So my question is, how easy will it be to extend this for directed networks? One centrality measure we know for directed networks is a page rank.
Yes.
Will something of that sort work?
Yeah, page rank, again, it gives importance to the incoming edges.
Yes.
So we could use the incoming edges as the basis and repeat the same
there
process.
is another version of page rank which adds a damping factor. So it's not completely weighted according to this incoming degree. But there is an extra damping factor also. So what with some probability you start this random walk for page rank, you can start randomly from some other vertex.
Yes, that's a good idea. I haven't thought about directed graphs for this one. It may need a lot of changes. So I'm not sure if the existing approach can be extended with some small modifications for directed graphs.
Okay.
But that's a good question to think about.
Thank you.
Welcome.
So tell me if this is true, or if it's not, tell me why it's not. So if I took something like a ring lattice, say 100 nodes, and they're each connected to 4 next to them. And if I just took that ring lattice and took one node and connected it just across the circle to another one, and just call it a shortcut. And the reason I ask this is infections and other kinds of spread, those kind of shortcuts are a problem because they can, you can obviously see it. It hits, right. Does that get picked up by this ranking algorithm?
Yes, will get picked up because the shortcut is to some faraway vertex, and that's the only way that faraway vertex is connected to the rest of the neighbors. So like you can use this graph itself here as an example. So this edge to 0 from node 5 can be considered the shortcut. So 0 is connected to the rest of the neighbors of node 5 through that shortcut thing that we're talking about. So it will get picked up. If you remove node 5, that faraway neighbor node is going to get disconnected from the rest of the neighbors of this node.
Okay, thank you.
We'll just thank Natarajan for a great talk. Thanks for talking today.
Thank you very much.
Thank
Good
you
luck,
all.
Mike.
See you all. Bye-bye.
Have a good one.